All right, this is a problem involving a polyprotic acid, an acid that's capable of donating more than one proton. In this case, the acid is capable of donating up to 2 protons, and accordingly there's 2 values of Ka. In general, when you consider polyprotic acids, only the first dissociation is significant in terms of concentrations. We're going to demonstrate that through this calculation, and we're going to consider the dissociations as separate steps. For the first dissociation, we have our balanced chemical equation and our equilibrium constant expression. All right, so here we have our completed ice table. As usual, water is a pure liquid, so we don't care what its concentrations are. It doesn't appear in K. And we're going to plug our equilibrium concentrations into our equilibrium constant expression. We see that unless we can make the simplifying approximation, we're going to have to solve for x using the quadratic equation. So we're going to test to see whether or not we can make the simplifying approximation. All right, if we multiply Ka by 1,000, we see the product is going to be less than our initial concentration of this acid, and therefore it'll be okay to make this approximation. So we've made our approximation, and we see x squared is going to be equal to 1.5 times 10 to the minus 5 times 0.5. What we're interested in is x, so we need to take the square root of each side. All right, and as a result of the first dissociation, we see that H3O plus ion concentration and the conjugate acid of the conjugate base of H2A are both equal to 7.07 times 10 to the minus 4 molar. Now we're going to take this quantity and carry it forward to the next dissociation. So we have here the balanced chemical equation for the second dissociation. So HA minus is losing an H plus to water and generating A minus 2 and an additional H3O plus ion. So we're going to finish the ice table and the equilibrium constant expression. The big difference here is that we already have some H3O plus ion from the first dissociation, and the initial concentration of HA minus is what comes from the first dissociation. All right, so we've entered into Ka the equilibrium quantities from our ice table, and we have a very complicated looking equation. We're going to test the simplifying approximation, and if that's valid, it's going to simplify our math immensely. All right, so we've tested our simplifying approximation, and we see that it is okay. We can breathe a sigh of relief because 1,000 times Ka is less than the initial concentration of our acid, and it's also less than the concentration of H3O plus. So in both the case of HA and in the case of H3O plus, we can disregard X when considering the equilibrium concentrations. All right, applying our approximation, we see that we can get rid of these X values up here, and when we do so, we find that we can cancel out these values so that we have X is equal to 5 times 10 to the minus 12. So now that we've solved for X, we can go back and answer our question. According to our ice table, X is equal to the equilibrium concentration of A2 minus, the ion that results when citric acid donates both of its protons, and we can see that it's very, very small. Okay, now we want to have the concentrations of all the other species. H3O plus is 7.07 times 10 to the minus 4 plus X, and we'll see that this X is negligible compared to the initial concentration. All right, and here are the rest of the questions answered. So the equilibrium concentration of HA- and hydronium ion concentration are the same, and we can calculate the pH as 3.15. Note that we are justified in ignoring the second dissociation because this is all that we get H3O plus wise from the second dissociation.